In 1980, the head of the Federal Aviation Administration was asked a simple question. Could twin-engine jets fly across the ocean? His answer was blunt. It'll be a cold day in hell before I let twins fly long-haul over water routes. That man believed what every aviation expert believed. Flying thousands of miles over open ocean with only one backup engine was suicide. The math seemed obvious. 4 engines meant 3 backups. 3 engines meant 2 backups. 2 engines meant 1 backup. 1 failure away from catastrophe. Today, that logic has been completely abandoned. Right now, as you listen to this, hundreds of twin-engine aircraft are cruising over the Pacific and Atlantic Oceans. Boeing 777s, Boeing 787s, Airbus A350s, each one carrying hundreds of passengers hours from the nearest runway, protected by a single backup engine. The 4-engine Boeing 747 and Airbus A380 that once dominated these routes are being retired, scrapped, sent to desert boneyards. The industry has made a $1 trillion bet that 2 engines are better than 4. But here's what keeps pilots awake at night. If that single backup fails, there's nowhere to land, just ocean for thousands of miles. The question is, why did we abandon the safety of more engines? Picture yourself at 35,000 feet over the Pacific Ocean. The nearest land is 3 hours away. Your pilot just announced 1 engine has failed. You look out the window at the remaining engine, that single turbine spinning beneath the wing, and realize everything now depends on it. This was the nightmare that kept aviation regulators awake for decades. In 1936, the rules were clear. Twin-engine aircraft could not fly more than 100 miles from an airport, roughly 60 minutes of flight time. The reasoning was brutally simple. Piston engines failed constantly. In the 1960s, jet engines were shutting down at a rate of 40 per 100,000 flight hours. That meant every single engine in the sky failed approximately once per year. The math was obvious. 4 engines gave you 3 backups. 3 engines gave you 2. But 2 engines? That left you 1 malfunction away from catastrophe. This thinking dominated commercial aviation for half a century. The Boeing 747 became the undisputed queen of transoceanic travel, precisely because it had 4 engines. Pilots had a dark joke they repeated like scripture. The reason I fly 4-engine aircraft across the ocean is because there are no 5-engine aircraft. Nobody questioned this logic, until Boeing did. In 1980, Boeing approached the FAA with a radical proposal. They wanted to fly their new twin-engine 767 across the Atlantic Ocean. FAA Administrator Lynn Helms responded with words that would become infamous. "It'll be a cold day in hell before I let twins fly long-haul over water routes." But here's what Helms didn't anticipate. Engine technology was evolving faster than anyone imagined. Modern turbofan engines weren't just incrementally better than their predecessors. They were transformationally more reliable. The failure rate plummeted from 40 per 100,000 hours to less than 1, a 40-fold improvement. On February 1st, 1985, Trans World Airlines made history. Flight 81O departed Boston for Paris, the first twin-engine commercial flight authorized to fly 120 minutes from the nearest airport. 11 FAA observers sat aboard, monitoring every system. The 767 burned 7,000 pounds less fuel per hour than the tri-engine L1011 it replaced. By 1991, something extraordinary happened. More passengers crossed the Atlantic on twin-engine 767s than on all 3- and 4-engine aircraft combined. The revolution had begun. But regulations and statistics are one thing. What happens when theory meets brutal reality? When an engine actually fails over the middle of the ocean? That answer came on a warm August night in 2001. Air Transat Flight 236 departed Toronto at midnight, bound for Lisbon. An Airbus A330 carrying 293 passengers and 13 crew members on a routine transatlantic crossing. The aircraft was cruising at 39,000 feet over the dark Atlantic when the pilots noticed something troubling. A fuel imbalance between the wing tanks. They followed standard procedure. They transferred fuel to correct the imbalance. What they didn't realize was that they were feeding good fuel directly into a catastrophic leak caused by improper maintenance. A hydraulic line had been rubbing against a fuel line for hours, slowly wearing through the metal. At 5:45 a.m., the situation turned critical. The fuel quantity was dropping far faster than consumption could explain. The pilots initiated a diversion toward Lajes Air Base in the Azores. They were 65 nautical miles away. They wouldn't make it on engine power. At 6:13 a.m., the right engine flamed out from fuel starvation. 13 minutes later, the left engine died. The cockpit displays went dark. The flight controls stiffened as hydraulic systems lost pressure. A small propeller called a ram air turbine deployed automatically beneath the wing, the aircraft's last resort emergency power source. Captain Robert Pichet, a former bush pilot with 16,000 flight hours, was now commanding the world's largest glider. A 152,988-kilogram aircraft with no engines, minimal instruments, and 306 lives, depending on his next decisions. Think about this for a moment. You're sitting in seat 34A when the cabin lights flicker and die. The engine noise that had become background suddenly vanishes. The captain announces both engines have stopped. The nearest runway is 19 minutes of silent gliding away. Pichet hand flew the powerless A330 through the darkness, descending at optimal glide speed, calculating whether he had enough altitude to reach the runway. He did. Barely. At 6:45 a.m., the aircraft touched down at 200 knots, far faster than normal landing speed. 8 tires burst on impact. The plane skidded down the runway, trailing sparks. Every single passenger survived. Air Transat 236 became the longest commercial aircraft glide in aviation history. 19 minutes, 120 kilometers, 0 fatalities. The system had been tested to its absolute limit, and it worked. But survival isn't strategy. Why did the entire aviation industry bet everything on just 2 engines? The answer lies in a desert graveyard in Arizona. Rows of retired Boeing 747s and Airbus A380s sit baking in the sun, their windows covered, their engines removed. These aircraft once represented the pinnacle of aviation engineering. The 747 flew for 54 years. Boeing built 1,574 of them. The A380 was supposed to dominate the 21st century. Instead, it became a $25 billion loss for Airbus. Only 254 were ever built before production ended in 2021. The 747 followed 1 year later. What killed these giants wasn't regulation. It wasn't public fear. It was mathematics. Here's the brutal economic reality. When Qantas analyzed their Sydney to Los Angeles route, they discovered operating an A380 cost approximately $305,000 per flight. A twin-engine Boeing 777 covering the same route, roughly $190,000. Fuel represents nearly 20% of airline operating costs, and 4 engines burn significantly more than 2. Maintenance costs multiply with each additional engine, but the economics only tell half the story. The real revolution happened inside the engines themselves. The General Electric GE90, which powers most Boeing 777s, produces 127,900 pounds of thrust. That's comparable to the solid-fuel rockets NASA used in 1960s space exploration. A single GE90 generates more power than all 4 engines on early Boeing 707s combined. The fan diameter alone nearly equals the entire fuselage width of a Boeing 737. And here's the twist that defies all intuition. These massive engines aren't just powerful, they're extraordinarily reliable. The GE90 has achieved a dispatch reliability rate of 99.97%. Its in-flight shutdown rate is 0.003 per 1,000 flight hours, 1 failure per 333,333 hours of operation. That's 6 times better than ETOPS certifications requires. Think about what this means. A pilot beginning their career today will likely retire decades from now, having never experienced a single engine failure. The Airbus A350 has now been certified for ETOPS 370. That means it can legally fly more than 6 hours from the nearest suitable airport on one engine. This certification covers 95% of Earth's surface. The 4-engine jets didn't die because they were dangerous. They died because 2 engines made them obsolete. Fewer engines, properly engineered, deliver higher reliability at lower cost. The industry didn't abandon safety. They redefined it completely. And in doing so, they transformed how humanity crosses the planet. The next time you board a flight across an ocean, look out the window. Count the engines. There will almost certainly be 2. This isn't recklessness. It's the result of 60 years of engineering evolution. The GE90 engine that powers most Boeing 777s has logged over 100 million flight hours with a reliability rate of 99.97%. A pilot flying today will likely retire without ever experiencing an engine failure. The old logic that more engines meant more safety was never wrong. It was incomplete. What matters isn't how many engines you have. It's how reliable each one is. And modern turbofan engines have achieved a level of reliability that would have seemed impossible to the engineers who wrote the 60-minute rule in 1936. The Boeing 747, the Airbus A380. These weren't killed by regulation or public fear. They were killed by mathematics. 2 engines burning less fuel, requiring less maintenance, achieving higher reliability than 4 engines ever could. Every day, millions of passengers cross oceans protected by a single backup engine. Against all logic, it works. But this story is just the beginning. Aviation is entering a new era of efficiency, autonomy, and risk. To discover what happens when the industry pushes even further, subscribe now. The next chapter is already being written.